asymptotic symmetries and kind of universal structures in the infrared within some of their Harvard. So superrotations and plot physics are going to be some of the turning light on, but a little bit. So the motivation for why we're doing what we're doing is essentially started off from the point of view of just trying to look at the asymptotic symmetry group of a flat spacetime and see if it's larger than what we had expected or what hadn't expected before. But in the end, what the title of the talk is referring to is a kind of secondary goal where the structure of the symmetry algebra that I'll talk about ends up hinting at perhaps doing this map from four-dimensional scattering to celestial sphere, which you can think of as like if you send a bunch of light rays out in the night sky or you look at the stars above you, that two-sphere would be the celestial sphere where we have some local operators that we want to map scattering states to. So by the end of the talk, I'll get into that. But what I'm going to first start with is this notion of asymptotic symmetry groups and what exactly happens in infrared in gauge theories, and even more generically when you have like massless modes and soft layers that led us to where we're looking at now. Okay. Okay. So the interesting thing is that there's this universal structure of relations between soft theorems that you study in quantum field theory and what actually started my sub-research program, this paper with Freddie Andy on a particular new soft theorem. And the relation to asymptotic symmetry groups, which is what I was talking about, looking for a larger class of symmetries compared to, say, just Poincare, or the superrotations are new compared to even larger symmetry groups that were doing in the 60s called supertranslations in EMS. And then memory effects, which are very low energy physical observable. So it's not a statement of I have these gauge symmetries and they act non-trivially on the boundary, so I should really consider them as like physical symmetries in my space-time. But they're actually just these corresponding low frequency observables that are kind of like the canonically conjugate paired modes to these symmetries. So I'll discuss this triangle first, and then we'll see this particular curious relation that I won't care about, which is related to angular momentum flux. So the whole point of the first part of my talk is just to set up that there is a universal structure that is there, and that by seeing in particular examples where different vertices were known and the connections between them, you ended up predicting basically this brand new iteration. So the simple example I'll start with is just the U1 case, and it turns out to actually have more interesting features with when you include magnetic charges, but I'm going to stick to the simplest case of just what you think of when you study an undergraduate EM with a charge particle and accelerator. You can see some of these like, features about interplay between boundary conditions that are appropriate and the symmetries associated with preserving those. And then the cool thing about what I do now and what is leading to this notion of maybe having this holographic description that like at least hinting that it wants to be there, is that for a particular case of instead of charge flux or energy momentum flux, you look at just like angular momentum flux. And there's actually a corresponding soft theorem that was recently discovered. Asymptotic symmetry group was proposed in, say, like 2003, compared to like some of the PMU and momentum case was for translations back in the 60s by Lonnie Spencer and Dax. And then the memory effect is also new. So it was fun because basically all this stuff in the last 5 years, or give or take a little bit, was a brand new iteration that had this structure predicting that. And so we learned something from there. Okay, great. So to start off with my example, I'm going to imagine first just flat space. In the end, I'm going to stick to this same diagram and say that it's actually like asymptotic flat spacing. But for now, just imagine that I take my Picasso space and I want to draw it on a piece of paper. And so I need to introduce some funny warping factors at the boundary. But essentially, the nice feature about a Picasso space is that the boundary is this null structure. So I have feature null infinity. And if I have massless scattering, I'm just going to have light rays that travel at 45-degree angle hitting that boundary. And if I have massive particles, they would go up in time and hit I+. And I have space like infinity at I0. So just keep the structure in mind. Now, if I want to do something like this simple example of electromagnetism, I have to know that I have, for instance, in gauge theory, a Gauss-Hall constraint. And what's fun about it is some recent results since then have kind of where you think that there wouldn't be some sort of constraint equation, you still have the same structure that we have in the gauge series. But this is a nice example because you know that if I have some charge matter distribution, oh my gosh, it says my time equals constant size, then I can say I know what the integral of the radial electric field is going to be far away. So in some sense, what I'm saying is the relation between matter and the gauge field, just from Gauss's law that you know of from undergrad. So, what do I want to say? Now I'm going to take my Cauchy slice, which has like, so my initial data in Cauchy slice has like symmetry, and I'm going to push that Cauchy slice up to null infinity. And then the fun thing about that is the data in null infinity are essentially like these, whatever charges were scattered in my space-time. If they say I look at massless charges, it's sort of fun because it's easier to do it, only looking at the thing, not resolving that class. I would have basically the radiation coming from them and then also the charges hitting. So the first papers that John and Jared worked on were essentially dealing with this kind of toy case of massless scattering and what we're looking at constraint equations on. This Cauchy says that we pushed up to fictional infinity. And last year, Okay, so since I have my charge, I have a linear vector potential for it, and I take the charge and then I accelerate it, there's going to be some radiation zone where if I'm really far away, I'll see essentially the kinematics of that charge. And the fun thing about the initial like soft layer memory effects statements is that if I have a charge that accelerates, then basically that radiation is proportional to acceleration, time interval acceleration of change in velocity. And so essentially, if I tell you my in-states which have a definite velocity and my out-states have a definite set of velocities, that data is enough to exactly tell you what some low energy observable is. So there's some component of the radiation field that is just determined by what this initial and final kinematics of charges were. So that's one way of saying why the soft layers naturally have this like soft factorization of like some factor that just depends upon like the initial final momentum of the external particles. And the amplitude with one extra photon, basically, from the radiation. So let's put some equations. So we were talking about schematics right now. Basically, in practice, what I'm doing, I'm looking at how my fields behave far away. So I could go the very formal route of saying if I want to do gravity and have this conformal factor, this conformal class of metrics with some omega. But in practice, what we, like the trick of the trade is just to look at a certain Bondi gauge or nice gauge choice and look at a radial expansion of large R so that the remaining variables are like the local coordinate along null infinity u and an angular coordinate z left of the celestial sphere. So if I do my expansion, then I basically have some natural boundary conditions that would basically be this sweet spot, the Goldilocks, between being too restrictive to exclude typical scattering, and too large to basically be a good initial outcome. So, for instance, right now, what we basically do is notice that like, there's a natural choice for setting A to R of 0, and then you can write just the electromagnetic field in terms of A, and A has a radial expansion. Now, there are particular gauge symmetries that happen to not die off at this boundary, and they look like they're A. And then if you do a mode expansion, I can look at the momentum modes and also this constraint equation, which is what I was talking about with you have some change in the AU, which I relate in terms of like some radiation you give. And this, so this is basically going to give you the Coulomb field, this is the radiation field, and this is the charge curve. So what I'm going to do, I can look at soft theorems, which tell me relations between amplitudes with or without an extra soft photon, and a fun exercise is just to look at like a textbook, for instance, Pascal and Schroeder, when they talk about soft theorems, they'll show that like when you guys achieve the soft theorem, you get this like Poisson distribution. And so the amplitude for adding an extra soft particle ends up being kind of related to the expectation value of that electric field. So you can kind of use your classical intuition just to like get some sort of feel for what it is we're saying, even though like you don't want to apply it for like more but essentially, so you have this intuition of how the radiation field is going to fall off at large R, and how in a typical scattering process you're going to get some sort of dynamical change in the gauge potential if it describes, like in this gauge choice, the flux of electromagnetic radiation caused by typical scattering processes are going to cause a shift in AZ, and when you see this in the soft theorem by just inserting A, knowing that A is a mode expansion, and when you take the large R limit at fixed U, you get a saddle point that localizes the direction of radiation to where you're sitting at this like sphere far away. So, in the end, like the first statements relating soft theorems to identities all amounted to plugging in the soft theorem into the constraint equation and showing that essentially there's this, that like you can probe from the radiation, this like the charge that generates large gauge transformation can be defined in a Cauchy slice that is future null infinity or past null infinity. You antipodally match it cost by naught, and the terms that appear there are essentially some soft part, which is this insertion of an extra like soft radiation piece, and then you have the charge set plus one, which you can matter particle related to them. So like the fun thing about it is essentially how I want to interpret it is like every time you get a software, you have some sort of notion of the fact that there is some low energy radiation telling you that, like in the classical theory, that the solutions have certain fall-offs of the fields that are maybe like in a certain 1/r expansion. You're probing that by looking at the radiation fields. And the fun thing is that the soft theorems also can be turned around and to like used to imply that there's this symmetry of your theory. So the fact that the charges for this large gauge transformation, or what I'll show later, which is the super rotations, can be rewritten using the constraint equations in terms of the relation between soft radiation and matter that fluxes through, says that if I have a soft theorem, then I have this like asymptotic symmetry state. So what I want to say, like that using that logic was what let us first basically motivate that super rotations, which were proposed as being part of what should be considered the asymptotic symmetry group of asymptotically flat spacetimes, was actually like reasonable to be considering. So I'll show you later the action and why maybe beforehand it was like us. But that was Freddie and Andy's sublating soft theorem stuff, which was great. So just to finish up this overview in the beginning, some notion of like you can go through like the canonical formalism and show that they actually do have a canonical conjugate mode between this memory I was talking about, just like seeing the net flux, which is a function of the initial and final momentum of the particles, and then a overall just baseline shift at any given point in the celestial sphere, I can shift up. So I noticed I was looking at this board a lot, so if I had any questions that were like raised, I could, of course, answer them, but I didn't see any hands. Okay, great. Okay, so now I get to summarize basically where we're at, and then get to talk about the fun stuff that I work on with super rotations. So all I want to say is that we have this ward identities giving us soft theorems of symmetries. Memories versus symmetries are essentially, the memory effect is a physical effect that is a statement about I just need the ingoing and outgoing kinematics for the particles, and I get out a certain low energy radiation observable, and they end up being typically, like, or in a lot of cases in 4D, canonically conjugate to this, the symmetries, the asymptotic symmetries that I will be studying. And going back and forth through soft memories is just a Fourier transform. So you're looking in frequency space, and you have this localization on the celestial sphere when you go to null infinity for massless particles. Great. Cool. And now we had that structure, and we had a brand new iteration with super rotations. So now what I want to talk about is a little bit more about this asymptotic symmetries called super rotations. So the arena here is a little more complicated in the sense that it's not just Minkowski space. We're going to go to what are called asymptotically flat spacetimes. So this was studied by Bondi, Metzner, and Vanderberg and Sachs in the 1960s. And to make it more mathematically precise, there's basically some notion of fall-offs at large R when you go to this boundary. So this, like, if I just plot a Minkowski spacetime, this is what I would have. And I'm imagining if I have asymptotically flat spacetimes and there's no black holes, so there's no horizons, then I still have the structure of the boundary. And so I can still, like, understand gravitational scattering from the point of view of, like, I still have this null infinity structure of my spacetime. And then the asymptotic symmetry group is defined to be allowed gauge symmetry, so just like say diffeomorphisms, mod trivial ones, which we say are the ones that fall off fast enough that they aren't affecting the structure of like your phase space defined in terms of the boundary data. Great. Cool. So now what I do, I actually like just go through the expansion at large R of the metric, right? So basically the first term here is just flat metric using particular coordinates for the celestial sphere and U as indicated. And then sublating terms, bonding mass, like you'd have this term just for like whatever Birkhoff's like solutions for spherically symmetric far away, and then you get radiative data. So the point here is that there's some extra integration constants if you didn't have matter field. And CZZ is supposed to be the notion of if I have just like a gravitational wave passing through, I'm going to be exciting this guy and its complex conjugate, which is appearing in CC here. And then you look at, just take a Lie derivative of this metric with some vector field and find which vector fields preserve that fall off. And so when you write it out, you get the term that here is a super translation and then this additional super rotation. Now what's fun about super rotations is that they kind of, so Christodoulou and Kleinerman studied like stability of solutions and have this fall off in large U that would kind of be butchered by super rotation. So when you do a super rotation, you end up
basically taking yourself through a finite superrotation to a solution that looks like asymptotically locally flat and essentially has like a cosmic string defect coming out where it's not quite holomorphic because you have a pole in your vector field. So if I just did rotations, then yz would be like 1z or z squared. So like the SL2C is the Lorentz transformations here. But the fun thing about it is basically, except for some funny punctures at poles, isolated poles for yz, I get that I could actually have a full set of CKVs be the symmetry like away from isolated points in the celestial sphere. And so the fun thing about this is then I now look like I have this asymptotic symmetry algebra that looks like what I would get for CFT2, like for the local symmetry algebra, not just the fact that the Lorentz invariance in the embedding space is global conformal invariance of the light cone limit, which is essentially what we're going to end up getting to. So the point of what's nice in 4D is essentially this like enhancement. And the fact that the reason why I talked first about the soft theorem stuff is that essentially you might be concerned about the fact that you're going to these cosmic string snapping solutions when you do a finite superrotation, so it doesn't seem to keep you in your phase space that you're starting with. And is that natural? And that type of question is a good one to ask, but then you can say, like, somehow this led to this soft theorem, and I do have that soft theorem in the scattering amplitude superapparativity with gravity, so in some sense you can turn it around and use it as a nice motivation for including superrotations in your asymptotic symmetry group. Great. Okay, at least considering that. So now, point it out.
Okay. So what's the physics of this impurity that you're...
So the physics of if you did a finite superrotation, it ends up introducing a cosmic string solution.
So I start with flat space.
Yeah, and I do a finite superrotation.
Yeah. I get a new solution of Einstein
equations with basically has this defect line. Yeah, and I think it's like whatever the energy density would be finite, so that where it's like infinite energy solution you would normally not. So I don't want to actually end up doing finite superrotations, but I kind of do infinitesimal ones around flat space.
Can I say a few words? Why do I expect that some big cosmic string that describes big information? What's the relation between cosmic strings and soft theorems? Because then you said that there's also some relations.
So in some sense, I think that the statement has got to be that away from this cosmic string, everything is like locally flat. I mean, like, so if you wanted to consider the like larger phase space that included cosmic strings, which is not what we're interested in, but it is good to know that like that doing that diffeomorphism is taking you to that type of solution. So then essentially when you're away from the defect, you're allowed to have a non-trivial. If I just wanted the sphere to be preserved, then I'd have global like SL2C, so I'd be much more constrained. So this local symmetry algebra is fine away from the it keeps yourself flat away from poles, but like it's, I mean, in some sense you're doing this diffeomorphism that's like wrapping some points on each other, so it's not surprising that there's some sort of funny curvature along a point where like basically you're rotating.
Normally I would say that I can do some transformation, but if they put some cosmic string, that's a new type of solution.
Exactly, so I'm saying it takes you out of. I would say that it does. It takes you out of this class of asymptotically flat space and takes you into asymptotically locally flat.
Soft theorem seems to be something very smoothly connected.
Yeah, so I would say that this is like the sense in which the symmetry that generates this ends up also giving you this like the subleading soft theorem, in the sense that if I do this diffeomorphism, then I get some relation between the metric modes and how do I want to say this? If I'm away from those points, then I think that that's part of the so even in other cases, like you can have like the gauge transformations do this funny like radial growth and still have finite like you can use these to rewrite the soft theorem for the case of scattering where you don't have those solutions, right? So I want to say that you're doing this antipodal matching, and somehow if you just end up plugging in these diffeos, then.
What is antipodal matching?
Oh, sorry. What I'm saying is that you have this expression for the action of this rotation charge on two Cauchy surfaces. You have one on past null infinity and one on future null infinity. And then you say that they're equal to each other, and that's where you get these relations between scattering states. And I'm just saying that if I look at the radiation for the soft theorem, then I can plug in basically what's in the next slide, what my radiation was and what my matter is. And so what I want to say is that this charge can be used to construct the ward identity using the soft theorem. I don't want to say necessarily that the finite action on the metric is taking you to the same class of solutions. But I want to say that in some sense, if you wrote down that charge, the soft theorem is enough for the case of scattering with like where you don't have these cosmic rings to give you back the equality that you need for this word identity. So that maybe you want to say that like, does that make sense? Like all of these quantities will not have like funny cosmic string solutions if you just plug it in. The question is because essentially I'm like basically doing a little deviation along this trajectory that would introduce a cosmic string for some choice of y. But I'm kind of thinking I can do it patch by patch or something like that. I have this arbitrary angle dependence. So,
sorry.
Yeah.
So, but, imagine there's an observer in that space.
Yeah.
And some kind of code that.
And I do a finite transformation. I'm looking at the algebra.
Will he fill it?
Say again.
So the observer that is in cosmic space will he feel the super rotations?
I think for these infinitesimal ones, you would only you'd see a local rotation. I don't think you'd be able to see the momentum flux.
And I super rotate it?
Yeah, no, I think the super rotation is going to be terrible at that point. Yeah. Yeah.
Can I destroy the plane?
I don't know the order of magnitudes because I'm assuming if you actually introduce whatever the scale is for that cosmic string, that energy scale, I think you're butchering your solution. Yeah.
Not physical because I've always had.
But I'm doing an infinitesimal.
Whether these are physical.
I'm saying if you do a finite one, I'm saying you could take the parameter to be really tiny, and look at just starting at flat space with no string defect, and doing a small rotation. Then I'm saying that somehow because. All I want to do is give myself the freedom to basically look at how I'd be able to rotate things locally. So for instance, if I have jets and I have reparameterization invariance and I'm able to basically define a different tetra for every jet direction, can I say that something screwy doesn't happen? Where I'm where I'm cutting between this is one jet, this is another jet, if I said that there are particles also going in that direction. So I want to somehow say that the question is similar to that. If I'm
it was an example to figure out if they're physical or not, which is something that I never understand.
So I want to say that if you do a finite superrotation, I don't think it takes you to the same class of finite energy solutions you want to consider physical. But I think there is a value in the sense that you can use it to see the sublating soft theorem in action, and the fact that you do have the if I give you any finite set of scattering directions, I can choose a superrotation to avoid those guys and look at that transformation, and that would be related to reparameterization invariance and scat. So in a sense, I can do that symmetry transformation on each jet direction, assuming that the jet directions are not somehow filling the entire sphere. So there's utility in it, even if you're not doing a finite. Yeah.
Do you know what order? Is it will there be a singularity in the solution at first order in this finite transformation? Okay. So
I have to refer you to the paper by Sasha and Andy. I don't have it in my head right now what it is. Basically, it's a Schwartzian.
When you take these lead derivatives,
CCZ changes. So CCZ would change by U dz squared yz, and yz so yz is 1 over z minus w or something like that. Then this is a full and it's order radiation term in the solution, for instance.
Okay, so at first order there is a singularity somewhere.
The news gets a finite amount in that gauge, but it's natural normally to do some sort of conformal transformation, when you describe the solution. So what Sasha and Andy did was they basically take the solutions that are studied in a different gauge where the round metric gets modified at the points of the insertion, take it back to this gauge, and then show that you get it looks like the news is constant, which would look like an infinitely radiating solution if you interpreted it too naively. But it.
Sorry, independent of the gauge.
I think,
is there a singularity at first order in this transformation?
I think it's it's a pole, a 1 over z minus w to the 4th times u for CZZ, which is the term in the metric, which is here, if I remember correctly. Here.
Okay.
Yeah.
Maybe I can ask a related question, but is there any relationship between the gauge parameter or the transformation parameter being finite or infinitesimal, and say the stress tensor associated to the defect in the solution where it does exist?
I think there is. One point I did do a computation of the TZZ that was defined in Parhar's paper, which I'll get to at the end, and in the background of this defect, and it scales whatever parameter they were using to describe it. So it had to be the mass of whatever energy density, but I don't remember exactly what it was.
Would you say that in the infinitesimal superrotation limit that this is kind of a probe defect or something? Is there some sense in which it really...
I think that the fun thing about it, so if I plug in 1 over z minus, like a single pole, then I end up getting back from this charge, the soft part of the charge is the stress tensor of the paper with Mitra and Andy Strominger and a couple others. So in that sense, there's a sense in which a particular probe, so this is a convolution in the sphere, right? So you're doing an integral over a different direction, so you're picking up all of the scattering points, and you picked a place to have the pole. So normally I would avoid where the particles are. But a particular one that does have a pole is giving you back the stress tensor as defined, as I will define later. So basically some soft mode that's convoluted with a particular reference direction where you're deciding to make it singular would give you the operator that when you look at correlation functions, it looks like the TO OPE in some sense, like the soft factor that comes out when you have a certain Rindler energy eigenstate, which is what I'll get to at the end, has the structure that the weight is there with the right pole and structure. So basically, the soft part of the charge looks like this is the stress tensor for a particular singular CQV. Okay. Any other questions? Okay. Yay. Okay. So I foreshadowed some things. Okay. So all I want to say now is that essentially the starting point was to use this definition of the superrotation charge, say if you find it in the studies of Barnash and Trezer, to write it as some out charge and in charge, which are these incoming and outgoing past and future null infinity expressions for this charge, which is defined in the boundary, but then a U integral and whatever. So you plug in the constraint equations, and you basically have a relation between energy momentum flux, angular momentum flux, and the radiation. So you can do that, and you can show that there is this charge corresponding to superrotation. So this is the charge, from a canonical analysis for the vector field that is superrotations. And in the scattering process, which doesn't include these funny backgrounds, so it's in flat space, you get this identity via the fact that the soft theorems are related to the matter fluxing through. So I kind of explained that before a little bit. And essentially here I have some soft part and some hard part, which is this I call the matter. So 0 mode of radiation because of this U integral, and integral of the matter system. Right. Okay, so again, I do my soft theorem. Then my soft theorem has a fun structure where it has a leading soft theorem and a subleading soft theorem, which was with Freddie and Andy did, and they also have a sub-subleading. And the point of this subleading soft theorem is that it's essentially, instead of a Weinberg pole 1 over omega, it's order 1, so omega to the 0th power. And also there's this differential operator from the angular momentum. So basically to project it out is a little bit different. So for the, when you have a 1 over omega, that's the Fourier transform of a step function, say. And so you can imagine that the one metric component basically shifts. So if I have the leading memory effect for gravity would be I have some stars collide and they radiate outward, and I'm sitting somewhere and I have another detector somewhere over there. And at some order 1 over r, we move apart by just doing geodesic deviation expressions. So you can calculate how much we'd move apart, and essentially until the next gravitational wave comes through, I'm going to stay where I am, and I'm going to shift by a certain amount. So you look at the initial and final difference of that, of my positions, that's the leading memory effect. To get something that's subleading in frequency, I would need to do an extra U integral or a U du integral. And so that's where there's something chiral to pick out to basically get rid of the fact that net translation would give you some infinity. If you said, I want to look at where I was compared to where I am now and integrate for all time, you'd get something divergent. But if I say something, I have to look at some chiral part that projects it out, then I'm fine. So we can find some memory effect that corresponds to the subleading guy, and it's all. But what I care about, mostly for what I want to look at with this notion of maybe some flat space lography, is just the structure of this vector field if I look at future null infinity. So when I restrict to scribe plus, say, I basically get 2 copies of the weight algebra. And so in particular, if I choose a y that is not part of the global, yeah.
Sure, it was perfect, but it's a little bit too fast.
Okay, no.
So, are you saying that the coefficient in the subleading term in the soft theorem is something that I will measure in some gravitational wave as some shift?
Yes. So sure. I'll be more specific. I didn't put the picture in the slide, but I can back it out. Okay. So the bonding coordinates are such that if I have like R corresponds to like null radial like geodesics, right? So if I have a fixed Z and Z bar, you have to be careful about interpreting in terms of like a geodesic sitting there and rotating or not. But say I had a ring that's sitting that is at fixed Z and Z bar, like some arc. When I have some collision process here and I'm rotating and I flux angular momentum through, if I'm sitting over there and I had basically co-rotating beams, every time, it's like a Sagnac effect that every time they go around this ring, they would pick up a little time delay, and then over time I would integrate it out, and it just happens to, you can show that that's the same integral that you'd want of this chiral part to project out the leading memory back and get back something finite, which corresponds to angular momentum flux through. So the basically it's like a Sagnac detector sitting at fixed Bondi coordinates. Like a ring measures the angular momentum flux through it, and there's a time delay. Otherwise, I think you can also write it as like a geodesic sitting there and it's somehow rotating with respect to like the night sky stars that are further away that the radiation hasn't affected. So I mean, there's a part of the game which, I mean, you have this constraint equation, so you have some sort of notion of a relation that has to, like, typically until you introduce these extra modes to be canonically conjugate, you would say there's some zero energy mode of the radiation that's a function on phase space for the charged or massive moving particles. So from that point of view, like this memory mode would be predicted by the fact that they have this GUZ constraint equation you haven't used. But the fun thing about it is you try to basically isolate what that observable is, and the observable here is that this angular momentum flux gives you some time delay. So, okay, cool. So the thing, and then that's the thing is like you could technically measure that. I think that in Amsterdam there was somebody who had looked into it, and they like kind of said how you would have in like with Einstein's telescope, like not actually measure it a single event, but somehow infer it. Also, like if you had like some E-laser or something with like a triangular array, then you essentially have like you could have counter-rotating beams and measure it that way. So even like the original memory effect is technically difficult to, you have to infer it from basically integrating how much you've been deflected over time to get like a net shift, say, unless you were in space and you actually like think of things as not having a restorative corresponding back.
Can I think that,
yeah.
So I get these signals in the gravitational detectors that are super wiggly and have all these frequencies, right?
Yeah.
And then this somehow should be something related to the lowest frequency.
Exactly. This is like the lowest frequency and the next lowest. So the lowest frequency is...
I go to the signal and I read out the first two Fourier modes.
Essentially, yeah.
What will map to the first two questions?
Exactly. Like the subtlety we want to say is that it's nice that if you do this chiral projection, you get rid of the fact that like the next subleading mode, I might be integrating something that's like a step function. If I integrate a step function, I get like whatever value of the step function times infinity if I integrate for all time. So there's a little bit of a trick with the projection, but exactly, this is like the first two leading modes, and they have separate. I have like one is angular momentum, one is energy momentum, conservation dictating them. So I think that somehow it's projected given the subleading. Okay, good. Okay, great. So now all I want to say here is that if I wanted to plug in a particular YZ, which is this pole, I would get back what some collaborators of mine identified as a 2D stress tensor. And by saying that, they're basically inserting this operator, which is some low energy mode convolved on this celestial sphere of the graviton field. And if you look at that insertion with some other particles, you would essentially get back what looks like a TOOP. And so the fun thing about that, which is what I want to emphasize, is that the starting point was to look at scattering in 4D and try to write a word identity for these like super rotations, say as an asymptotic symmetry of 4D. And in the end, the same expression, the soft part of it's used to write what looks like a 2D word identity. So essentially the theme, even though like I'll be focusing on super rotations of a lot of the work that Andy and collaborators have done, is to show that like this asymptotic symmetry structure, like these what they call large gauge transformations, which are not like some, it's a little different because it's supposed to be like the gauge parameter has some sort of independence at each angle on the sphere rather than some non-trivial winding, have the same structure as like local symmetry algebras in a 2D theory. And we're trying to basically build up the map, and a key important step was noticing that when they noticed that this stress tensor, there's some notion of a stress tensor that seems to be natural for the 2D. So where we, like Shuhong and I and Andy went with this is to basically say, in order to actually make the statement, there's something that's been swept under the rug. These HK here's are coming from like UDU, or the field. So in some sense, these Rindler energies are like EDE. And so it's not like the standard plane wave energies, like the derivative structure that appears in this, like the angular momentum operator is something where you actually want to change your basis from plane waves to what we end up describing as not high space states, but conformal primaries. So that's where I'm going next. Great.
That's good.
Yes.
You said these vectors satisfy Euclid algebra. Is that just the Lie bracket?
So here, I'm just looking at the Lie brackets of the vector fields right now, and like you want to maybe look for central extensions or something like value C.
Yeah. Well, is there any sense in which those generators are metric dependent? Like, do they depend on any part of your expansion of the metric?
I would hope that like somehow. Like they're definitely, this is coming from the fact that like you're looking at asymptotic symmetry groups for a particular metric, but I do think that you do have to be careful about like commutation relations between doing a super translation and a super rotation don't commute. So in that sense, I guess you have to like take that into account.
Yeah, usually somehow the metric dependence, like when you want to look for central charges, that sometimes is important.
So there's a recent paper by, like words like that are used differently. There's a recent paper that was looking at double soft limits by like Ralph Luhager and collaborators that I can tell you what they did, but it's a long paper and I have to read it again before I like say what they exactly conclude. But I would say that this like holomorphic structure is just coming from the fact that you don't want to ruin the round sphere metric at like away from points where there's like singularities. So I mean in the sense that like the YZ being just 1 Z and Z squared is just SL2C global conformal Lorentz invariance. And then I agree with you that like in principle, if I did a super translation in addition, like on my metric or in a super rotation, like then like those don't compete with each other. And so like I would assume that would basically say that I have to be careful when I keep beyond like the 0th order terms. So right now, I mean, like technically this vector field will have a CZZ or something appearing later, but I'm looking at linearized space right now, so I don't.
Okay. Well, the other place that you see the central charges is when you do the actual Poisson bracket. So do you do that for the? So
we were like standing on the shoulders of Barnett and Tracer, as far as so most of what we were doing was linearized charges. And in that case, no, but you did like so the kind of trick of the trade is to describe the memory effects by taking the quadratic pieces and putting it on the right-hand side as the effective stress tensor. And so in equations before I was like hiding that under the rug, where I want to say that like the matter part is really not just the like linearized soft photon shift, but the quadratic pieces are part of what I'm considering T is the source for that. So, and I think technically that's the way that would have justified the leading memory effect, but like there will be like non-trivial like quadratic terms that appear here that I'm not writing down, or terms in psi as a vector field that depend on the metric, because I'm doing like a derivative deeper in the metric and I want to preserve.
Sorry, I think I lost you.
I'm just saying I think that it matters at the linear order that I'm mostly concerned about. It like the terms I think will not reappear.
In the Poisson, if you like did the whole symplectic structure or whatever.
I think if I took a look at terms only linear and C, I think that I would basically see that like I do this diffeomorphism and I shift C by an inhomogeneous amount, which is what I first care about with this, like what I was saying, this UDZ cubed YZ. And then there's also like whatever rotation of homogeneous piece that's quadratic in the charge.
Okay, I think I was asking you if you tried to realize this algebra in the Poisson bracket.
Yeah, and I think that it has been by Varnish and Tristar, but we didn't need much of it except for like the zero, like the inhomogeneous shift, which is a statement that there's
central charge.
I think that there's like I think that like the people who were studying it didn't get at least the expected. The extensions, from what I remember from the paper, were not in the like the TT part. I thought. There's some sort of super translation and super rotation combination part that might have been at like a funny co-cycle structure or something, but I don't remember the result because I wasn't. But I can point you to a reference that does look at it from that point of view more. In the past, they were just doing like they weren't looking. This person looks at soft theorems and double soft limits to answer the question. Great. Good. Okay. So what I end up doing, or what we end up doing, is looking for basically solutions that behave in a covariant way when you boost in a given direction. So you pick a reference direction to boost in. And then there's solutions to the Klein-Gordon equation for the scalar case. And essentially the fun thing about this is instead of looking at plane wave solutions, it's going to be some superposition of plane waves that end up giving you this kind of non-trivial weight factor out front. And to do that, there's a certain cute trick, which is basically if you go to momentum space, and I use a bulk to boundary propagator, I'm just trying to turn everything to be SL2C covariant with like a reference direction, which would, if the weights were integers, it would be like a highest weight state. But in this case, actually, we find the weights have to be principal series. So it's not quite the standard representations of like what the adjoint is for the Li. So, okay. All I want to say is so I started with this thing where I had the stress tensor, and I had the soft theorem, and I wanted to basically diagonalize it, finding these HKs. To do that, I had to go to these states which have this funny behavior under a Lorentz transformation. So the reference vector changes like you would change a point on the complex plane when you do an SL2C transformation, and the X just gets a boost, and then I get this factor up front corresponding to whatever weight is here, and the dimension of this. Okay, so now I went to momentum space and said that I can look at particular hyperbolic coordinates for this guy and show that because I know that this reference vector, when I change it, changes this particular null guy. So I'm doing basically embedding space formalism in momentum space now. And so I have this 4 vector, but I have it parameterized in terms of this plane. And then it's just cute to notice that the bulk boundary propagator in ADS is exactly what you would need to turn these plane wave states into states that had the weight property that I happened to specify before. So essentially what I'm doing is I'm doing a bulk boundary propagator for my solutions to the Klein-Gordon equation that's massive by taking like a given on-shell hyperboloid, which is what I care about for the scattering matrix for massive particles, say, and just bulk boundary propagating along that to smear the plane waves to give me back ones that have this appropriate dilation with respect to some reference vector. So what happens here is we have this notion of some TZZ that looks like it would be the stress tensor for 2D CFT, but that would mean that you need to have some notion of local operators in this 2D CFT you'd like to. Even for the case of if it's supposed to be generic and not just massless scattering, like you have to associate some point in the celestial sphere for a massive particle. And so one way to do that is essentially to take this smearing of different momenta and do that. Versus if I have a massless particle, there's a sense in which it goes to a point in the celestial sphere. So I have a much more natural way of associating a point with just like the direction it goes. Right. So you can define things that way. And the fun thing about doing this is that you want to just double check that there's some like a completeness relation. So you'll need the half real line for this principal series because the shadow operation basically flips the weight to the sign of the imaginary part. When you're on the principal continuous series, you can just show that this use results from various CFT papers, which tell you that certain integrals of bulk boundary propagators are complete or orthogonal. And
Nu is the energy of the particle?
Nu here is a weight that is exchanged for the energy. So what I want to say. So if you look at this, like what I'm doing is essentially taking the energy and integrating it with this profile. So whatever appears, like the point on the hyperboloid is its energy up to rescaling by the mass, which is like the overall size of the hyperboloid, the curvature. So like I've replaced that with a continuous parameter, which is this I nu here, which is not the energy, but it's the same like real parameter that you need to parameterize like, solutions when you've given up energy. You use a Fourier transform basically. So a Fourier transform might exchange energy for U, and in this case, the Mellin transform exchanges the energy for nu. So it's the weight. It's not the energy. Okay. Okay. That's fine.
I'm trying to understand the notation. So M.
Okay, so M is the mass of the particle.
Mass of the particle.
And I've stripped it out.
On the right, where is M?
M is probably stripped out or set to 1. Hopefully, it would just dilate things and rescale it. So maybe this equation you might be pointing out something there. But in the paper, hopefully, everything should be taken care of. But basically, the mass is just overall size, so I could rescale it into X if I wanted to keep track of it. So imagine that my measure doesn't have the M dependence here. I think that it would normally just like basically pull out here, but I can shift it into X if I wanted to, just the same, and then do it.
A CFT with a continuous parameter?
Yeah, you do. This new is the continuous parameter. It's a weight. The weights are principal series weights. But I think you did point out that the mass is kind of...
It was the inverse of that relation.
Exactly.
Plane wave.
Is a plane wave, yep, of these G's. Exactly. So...
And there delta was max 2.
Delta ends up being in the principal series. It ends up being D. Like so at first you basically let it be whatever it is, and then you find that if you're in the principal series, you basically have this nice completeness relation. The functions are like the same plane wave scattering functions can be turned into these principal series guys, and you're including everything. Like they're normalizable in the sense that so basically if I do this transformation, if I took the Klein-Gordon product of two of these solutions, I would basically be doing an integral of two of these G's. And if I want that to be finite, for instance, then I'd be worried that one of them might have this like funny power behavior. I'd like do that convolution. But in the principal series case, at least I get this nice delta function the same way that I would. Okay. So like what I'm using here is essentially this type of orthogonality, and there's two solutions. But if I restrict nu to being only a half real line, then I would kill one of them. So I would get just some orthogonality in the news, for instance. Or in this case, if I take a complex conjugate for the Klein-Gordon norm, then this term would probably be the one that contributes. So I would get just the delta function like I would have for two particles with momenta going in one direction and staying and going that way forever. So weight on principal series, based on position, and doing some...
Describe a little bit the physics of these incoming states of plane wave. We understand what it is. Right?
Yeah.
So what is this little bit?
It's just a superposition of plane waves weighted by the Boltzmann propagator. So I would say that for the massive case, I don't think it... Like I don't think there's a sense in which it looks any nicer. It dilates nicely if I have the reference direction be in a certain position and I boost towards it, it's going to rescale nicely. So in that sense, it's because what I'm saying is I'm want to do basically SL2C around or like global conformal transmissions or like around that point, like boosting around it, rotating around it. Then it behaves in a nice way. Versus I can imagine a plane wave, unless I'm like going along the direction of the momentum. I guess that's the analogous special place. I think so. What I would say, which is, like, instead of trying to visualize what these plane waves look like in the massless case, you can just do a Mellin transform. You don't have to do this angular convolution, so there's less of a trick for that. But the fun thing about it is, in either case, you end up probing the solution at all value, like the S matrix element, at like in the deep infrared or not infrared for the massive case, but in the deep UV, say for instance. Which is kind of funny, right? So if I take like a scattering matrix element and I say I've computed this in an effective theory, and then I say that I want to like transform this S matrix element to these high state basis, I need to basically know that function, the S matrix element is a function of like all momenta. And so like Thomas Taylor and some others look at like the extra profile, like if you look at a string amplitude, they actually did the Mellin transform on the form factor that appears there to capture the UV behavior. So
very high momenta is probably very small resolution in the sky.
Well, like you would hope, yeah. But the thing is that high momenta in different directions are all like added up. And,
We're saying to find some state in the celestial sphere, even for very big angles, I would need to know all the momenta. I think that in the sense of whatever the Boltzmann propagator gets tapered off, and that's probably when you like look at that. But I mean, I am saying like you're summing up, like you're weighting it with the Boltzmann propagator, like the solutions. So if in this whatever intuition that gives you, I don't know if there's anything more like I want to like say I'm visualizing what those plane weights are. Okay, so then I just made a brief statement about the shadow giving you a linearly dependent solution when you want to isolate what the actual complete basis is. And then the next statement is just that in the massless limit, this is somehow analogous if I take the frequency to be m over 2y, and y being a coordinate as I go to like the ADS boundary,
then I can see that the limit of the bulk to boundary propagator, the fact that there's a contact term, kind of motivates where if I just did a Mellon transform on my plane wave, I would get back another highest weight solution, or not highest weight, principal series solution, conformal basis solution that is relevant to scattering. So what I want to basically say is that when other people were looking at some notions of like class crystallography, one natural thing that De Boer and Salukin, for instance, started, and then Clifford Chung and others have been working on also, is to take Minkowski space and to, so let's sort of foliate it. And so in that situation, then you're basically doing field theory slice by slice. And if you have some sort of conformal field theory that you're starting with, then there's a natural notion of maybe like doing the, like effectively looking at a theory on each slice and then integrating over all slices in the end to reproduce correlation functions that have like the same structure that we have. But the fun trick about what we're introducing is basically that we're just saying, this is the transform you have to do right on the momentum space amplitude so you can apply it to ones you know and like see if the structure is nice or see that things are what they are or what happens. So, so massless guys are this thing. And then all I want to say is we can do the same thing for the photon and graviton. You basically have some sort of notions of a natural gauge choice being like x dotted into A being 0 and harmonic. And like how you want it to transform if you boost and change the reference direction. And you get the Jacobians for the indices. And you can do this in more than in 4D. You can do it to like other dimensions. Same thing with graviton. And in these situations, because you have the two helicities, when you do a shadow, you would map it to the opposite helicity. And actually, for the Mellon transform case, the shadow doesn't take you to the other Mellon transform solution. So, great. So what I want to basically say is that the kind of fun thing is when you look at for these conformal primary solutions, they're motivated by this sublating soft theorem looking like a stress tensor in the 2D case.
Sorry.
Yeah.
Is there something special about fast and future? Should you have one sphere for future, one sphere for fast?
So the one fun thing about it is that might end up, from the way that the T is defined, when you do this charge matching between a Q plus and a Q minus, I think you'll end up getting a difference between like a future and past guy that is the symmetry T. Like you shouldn't necessarily like naturally separate them. But there is a sense in which, so say I take 2 to 2 scattering in massless, there's the kinematics constrains you to being on a celestial circle instead of any point in the sphere, just massless scattering 2 to 2. If I choose which ones are in and which ones are out, then I get the same function with different ranges of the cross ratio being between 0 and 1, or between 1 and infinity, and like less than 0. So I don't think it's conclusive at this point whether or not like you only have some notion of like stress tensor out minus stress tensor in is like the stress tensor like T that we've defined in the soft theorem, rather than separate celestial spheres. But the kinematics probably indicates that something's kind of fishy with low point dynamics. So maybe there's a resolution.
So does the antipodal identification you're doing of sky affect these hyperbolas in any way?
So the identification ends up being at the boundaries of like the de Sitter region. I don't think it ends up mattering too much because in the end, like the quantities that we care about can have contributions from the just different regions, and are not like there's nothing butchering. Like we're not doing like that thing actively. We just have a quantity that is one integral and another quantity that's like the matter part of it that are related by the symmetry. Okay.
Sorry, my question I think is naive. It's just I'm really confused. Like, would we like to transform amplitudes into this language of Z-bar, and then interpret the correlators in Z-bar as correlators in an holographic?
That was the hope.
That would be the
hope. That would be the hope. Right? But the thing is that for low point amplitudes, you can kind of see where things start to go awry just because of low point massless to massless. You need to go to 2-2 signature to have a non-trivial 3-point function. You need to set like the Z-bar variables all to be equal or something.
When Z-bar approach, it would mean that the 2 points are closed in the sky, right?
Exactly.
So if they are both close in the future, it's like a jet, right?
But also if they're close in the, I think you still get some singularities. Like, I mean, just like like if you do crossing symmetry in the amplitude, like the P1.P2 up to like I think there's collinear singularities even.
Maybe I'm confused, but I thought that you scatter like 4 particles, and then you have 4 incoming particles, and then 5 outgoing particles.
Yeah.
And if one of the 5 outgoing particles in the same direction as the incoming, that will be not special. Yeah. Am I wrong?
I think if you just have P1.P2 and I take P1 to have negative sign, I still get.
You're not wrong.
Okay. What I want to say is that the massless scattering, if I have P1.P2 and I have one energy opposite, I'm just solving the dot product being like 1 minus P hat dot Q hat. And so I guess you get a plus sign and you're saying it's 1 plus P dot Q. Wouldn't there be opposite cosine? Like 1 minus cosine theta? Okay, my massless scattering and I have a pole like 1 dot P dot Q. If I change the sign of the energy in one of them.
And the point is that in the real space of mathematics, these are different regions. So you really have to use crossing to complexify momentum to connect one to the other. And then...
No, but you're like...
I would imagine that in your CFT, perhaps there are two types of fields. Some Q positive corresponding to stuff related to plus infinity, something to minus infinity. And they would have non-trivial OP if they are both at plus infinity or both at minus infinity, but otherwise... No,
but like I'm saying, like the soft theorem in some sense is attaching to both incoming and outgoing lines. So in that situation, I still get a 1 over z minus w appearing from either of the two. And so that's the sense in which, like if I have an outgoing soft graviton, which is what I'm using to construct TZZ, then I need to hit both the incoming and outgoing particles on that. So like that's where...
That means adding an extra soft particle, which is called...
Also in the past. Sure. No, but in the sense that, okay, if I have an outgoing, only outgoing, then I attach to both, and I think I still get the pole from either of those, is what I'm saying. Right? I mean,
maybe
I'm just like, maybe I'm just like one.
Adding an extra, or the collinear graviton is adding an extra graviton to each of your particles, right?
No, I mean, like, if you add absolute contributions from each, the soft theorem is the sum over each of the incoming and outgoing particles, and
you add two parallel and going to the future. Or two to be parallel and going.
No, I have an outgoing future guy when I just have P dot Q with opposite sign, right? And if they're both massless, then I would get, when I get like one, like plus or minus 1 P hat dot Q hat, and there should be some theta for which P dot Q is plus or minus 1, and so the plus or minus 1 is the energy, whether this positive.
So you said there is a similarity when
think there, right?
Collinear, but one is at minus infinity, one is at positive. That was what
I think so. I mean, maybe I'm being really silly right now. I'm just saying P dot Q, they can have opposite energies and still have a Z minus Z, like Z minus W singularity, right? Cosine theta, 1 over P dot Q.
Maybe we can discuss.
Okay, I mean, whenever I'm just doing a dot product of two massless momenta with different energy signs for the first term.
Let me even say it. I'm talking about locality, right? Things are local, but it's hard to imagine that something is local if something happens at minus infinity. Being local is something that's happening at plus infinity.
There might be an antipodal difference, but I'm just saying, like, if I have a plus or minus sign here, and I take the dot product, I'm going to get minus or plus 1, like plus P hat dot Q hat. And this is just cosine theta. And I'm saying that there's some angle at which this is 0. So I have a pole in the soft theorem, for instance, like of that form. I would get some collinear. Sorry, that's all I meant. And I hope I'm not like completely butchering like whatever trigonometry right now. But like okay, good. Okay. So I'm fine with all this. Great. Is it for the gravity? Ta-da. Fine. Oh, going the wrong way. That makes sense. Okay. Good. Okay, so amplitude transformations. I just made the statement before about doing this transform directly on the scattering matrix elements instead of going to this slicing. But in the end, now we are looking back at the slicing and trying to learn about it. For the mass, you can just do this for some particular amplitudes for fun. If you choose some particular kinematic configuration, so you have a massive particle that barely splits into two, then you've artificially made it so that it's local in momentum space in the sense that I do this convolution in momentum space, and if somehow momentum space were my physical spacetime, then I have like these Witten diagrams that I'd be computing, and you know that those give you the right structure of like the 3-point function for a CFT. And I can artificially make that happen in this physical scattering process by just having a particular decay process where the masses are so close for the daughter particles to the sum of them being equal to the original parent particle that they're kind of local near each other on this celestial, on this location on the on-shell hyperboloid. So that was just one real example, and you can see that there has to be this right structure, just Lorentz invariance. And then when you go to the MHP amplitudes or massless amplitudes, I just do a frequency integral over with some power, some Mellin transform of MHP. There's a non-trivial thing that changing the energies changes the locus of momentum conservation. And this makes some of the low point amplitudes 0 unless you're in 2-2 signature, so like contact terms only. And just a fun visualization of that is essentially you have this overall dilation weight. So if you have a conformally invariant theory, then you would have that dilation eigenvalue basically gives you a delta function for the sum of the weights. And so it converges in that sense like in a distribution. And then you're playing a game of different energies for different external particles, and it's deformed, like closed to form a null polygon. And so essentially for low point amplitudes, you localize to some particular solution where if I fix the directions, the relative sizes of those lengths of the arms are fixed by the closure property. And then I just read off these omegas equal some function of the z's, plug that in, and get back my 4-point function. And it has the same form you have in the big yellow book, except for this funny thing about kinematics telling you it's only imaginary real cross ratios. So it's somehow, what we hoped is that somehow if we had these simple examples of some theory where I just do this transformation, then I could do a conformal block decomposition and try to recognize different properties of the CFT. And if you go to lower dimensions, so Shuheng Xiao and others did do a little bit of a 3D conformal block decomposition, so the kinematics don't get in the way in the same way, and show that whatever optical theorem in 3D gives you some positivity properties for the conformal block decomposition. So stuff like that. Since I'm basically out of time, all I want to say is essentially what's interesting about this stuff is that it's easy enough to do some sort of notion of a map that makes the stress tensor look like it is acting on a state with a given conformal weight. But you really see that the abstractions to interpreting it, this is nice, these scattering states or these local operators in some CFT2 is just even kinematics, momentum conservation in the 4D theory is somehow getting in your way. So there's two routes to this. If you want to actually just say that you can try to look at collinear limits without, in larger point amplitudes, and somehow, Thomas Taylor and others are working on that. Or you can try to play some funny games with taking a conformal shadow of the outgoing states first, and because these are also satisfy the same properties you want for the solutions from the point of view of the sublating soft theorem, you can basically make the 2-point functions be the standard 2-point functions in the CFT2 rather than a delta function. And whatnot. So there's bits of games to play, but I think that the best result and the thing that's being worked on right now mostly is that in the there's a notion of conformally soft, which is zero frequency translates, except for some funniness with this momentum conservation saying that you get localized to frequencies that are non-zero. If you have a high point amplitude, you can dilate one of the energies all the way down, and when you do that, you're basically essentially picking up the lambda goes to zero limit. So there's this notion of conformally soft. And when you study conformally soft modes, there's a story that's being developed by Strominger, Poom, and Donnet, which is looking at kind of extra different weight solutions that are in this principal series and off the principal series and correspond to the prefactors that appear in the stress tensor. So basically, we're exploring that right now. We're basically looking at does this conformal story going to this basis, which was to handle just arbitrary energy scattering states from the point of view of these are the things that are in the S matrix before you add the soft graviton. Does it tell you something back about the soft modes that we care about? So, okay, that's fair.
Any more questions for Sabrina?
So what is known about the 4-point functions?
So,
what are the axioms that I would like to bootstrap them directly?
I think that we don't have a nice formulation in the sense, because we don't even have a nice 3-point function. The 3-point functions are, I would think I would take Yang-Mills theory or something and do the map and then say that I have these Mellin transform states as my operators. And if I do that, then I would see just the 1 to 2 point scattering. I think there's a subtlety that hasn't been addressed, which is how to understand maybe in terms of 2 CFTs instead of 1, what goes on, why does kinematics in 4D seem to get in the way of having a nice interpretation in terms of 3 operators come together and their poles and their
3-point function probably just conformal invariance to dictate this.
No, and there's delta function. Right? I'm going to say the 3-point function is collinear for massless scattering unless I go to 2-2 signature, and then global conformal invariance gives me.
If you go to 2-2 signature,
2-2 signature, then for half of it is. So it's you could 2-2 signature. I have 2 solutions. I can say in the same way that the spin helicity variables, you'd have to pick Z all the z's equal to each, like the brackets, square brackets or angle brackets to be parallel to each other. The analog here is I choose either all the z bars to be equal or all the z's to be equal. And then in the other half of it, so the z and z bar are now independent real coordinates. The other half looks like the SL2R dictated standard 3-point form. So when I say that we've been approaching it more from the point of view of just do this transform and act on whatever you know and see what happens. And I don't think this is elegant because there should be some notion of like, we have super translations too. Where do they appear here? And part of it is translation, and translation invariance is giving us momentum preservation, which is, kicking us in with this. So, like, I think that it hasn't been fully settled exactly, like there's some ambiguities in the map, and then also like, maybe what do we expect? Is it fine that because we have these like translation invariants in the bulk, it's giving us something funny with the low point amplitudes, but somehow, no. I don't know.
Yeah, so since you mentioned that the systematic, the end to the KMHP
yes.
Has been studied, a big difference between the maximum Helicity divided in case and the case, say, where you preserve Helicity, is that in the first case, you don't have multi-particle poles.
Yeah.
So 3-particle factorization is not allowed. But in the other cases, there is, say, a 3-particle factorization. So do you see is there anything in particular that you see in these correlators that is telling you that one thing is very different from the other?
I would say that I think the thing is that we were starting from the point of view of looking at scattering only the S matrix with like 1 to 2 scattering or whatever, I guess you could decay. And I think that like things like that, and also like because Thomas was indicating something along those, I should really just try to look at subsectors of 3 operators coming near each other without the so I can avoid this momentum constraint. And I haven't looked at it enough yet, but I think it's.
But in principle, from this paper.
Yeah. This paper, one would hope that it would have to have something like that, and like, I mean, in some sense, like when these, like the forms of the correlation functions for like. Are mostly coming from Lorentz invariants in the bulk. So I mean, I do think that there should probably. I think I should look at that. I mean, because I think I just like I kind of like stopped as soon as like what I was hoping would be the map with only a single CFT, low point amplitudes, and I would get the structure that you like is the bread and butter of like starting with 2D CFTs would work out nicely. But I think I should just look at subsectors and operators near. So I'll go look at it, but I don't know. Sorry.
Any more questions?
So, the super rotation chart was related to this stress tensor with Sebastian Spitzer. And there I don't recall, did you have a central term? Like, was there
no, and this is like the question that. So I can refer you to a recent analysis of this, but I haven't digested it enough to, I guess, summarize it adequately. But this paper claims to look at double soft limits to try to address that question. So 1808. Okay. But I don't want to say vouch for it, but I'm saying that other people are addressing this in a more, post cycles. Anyway. So I was reading this before. We had a wonderful lunch conversation.
Yeah, I had a really question. So maybe you said this at some point, but what do the super translations do to these correlation functions of operators in distributive dual 2D CFT?
The super transitions, what they do? I think that, like, technically we know what they have to do because we know, like, the Lie derivative that we're taking. But I don't think that we've actually written it down in so much. Like, what I want to say is that there's a sense in which we have, like, U1s giving you Kit smoothies in this, like, 2D thing because, like, the current algebras that have been worked down in some things. We have these super rotations seeming like the soft theorem giving you the stress tensor. But we also have this gravity, like, so gravity in the bulk is giving you a super translation vector, too. So I think that, like, somehow there's a, like, no matter what field theory you have on this boundary, you'd always have super translations if you also had super rotations, too. So, like, I think that would be an interesting point of view to start from is that, like, you have this symmetry algebra that includes T, or, like, yeah. But I don't, like, we haven't addressed that yet. The way that these guys handle it, they do seem to talk about the full gravity side of the algebra. So, yeah, I feel like it should give you funny restrictions because you have this, like, abelian or on its own symmetry there that doesn't commute with the rotation.
So in 2 plus 1 it will be an angle plus a continuous permanent.
So in 2 plus, it should be something like whatever, like diff as one. The issue I want to say is that some of the subleading soft theorems, if I guess I in lower dimensions, I'm fine doing the symmetry analysis of like conformal transformations or talking about these Mellin transforms of amplitudes. But I'm slightly wary of the soft theorem stuff just because I don't have propagating. But the people have studied 3D EMS type.
Okay, I think we can wrap it up for now. So let's please breathe again.